Hi, welcome back everybody. For this video we're going to be taking a look at part 2 of the 8-5 notes. Now in part 1 we learned to define the tangent ratio for an acute angle in a right triangle. And we said that the tangent ratio for an acute angle in a right triangle, like angle A here, is what you get when you divide the length of the leg that's opposite the angle by the length of the leg that's adjacent to the angle. And so we did one example where we found the tangent of a couple angles in a right triangle. Today we're going to be taking a little bit of a closer look at this idea of the tangent ratio. And we're going to be using this information, this idea of the tangent ratio, to find some missing sides or missing angles in a right triangle. But first of all, let's follow along with me here as I think about this idea of um, tangent ratios, and I connect it to something that we learned a while back about triangle similarity. So first of all, step one, you'll notice that in this diagram over here, triangle ABC would be similar to triangle DEF because of angle similarity. We know that angle C is congruent to angle F because they're both right angles, and we also know that angle A is congruent to angle D because they are marked congruent. So we have two pairs of angles that are congruent. So these two triangles are similar by AA similarity. And this means that if I take a look at the ratio between A, which is the length of BC, over D, which is the length of EF. Now that's a pair of corresponding sides in this similarity, right? So if I make that ratio of A over D, it should be equal to another ratio of corresponding sides. In this case, I would do B over E. So A over D would be equal to B over E by the definition of similar triangles, and this idea that in similar triangles, corresponding side lengths will be proportional. So we set up the ratio of corresponding sides here with A and D, and it would be equal to the ratio of corresponding sides here with B and E. Now if this proportion is true, then so is this one. If I take A and I switch the B and the D and make it A over B equals D over E, that's going to be a true proportion so long as this first one was, right? So I just took this proportion, rearranged it as A over B and D over E. Now if I look at this idea right here, if I look at the proportion that I have here, this first ratio of A over B, that should look maybe a little bit familiar because from the perspective of angle A, side length A is opposite and side length B here is adjacent. So this A over B is the opposite side for A over the adjacent side for B, or sorry, for A. And that means that we are looking at the tangent of angle A. A over B is the tangent of angle A. The second ratio, D over E, well, something similar happens there, right? Because D is opposite angle D, and E is adjacent angle D. And so D over E is opposite over adjacent for angle D, so that means that D over E, or the second ratio in this proportion, is the tangent ratio for angle D. And so the conclusion that we can logically draw from that is that if the measure of angle A in a right triangle equals the measure of angle D in another right triangle, then based on this kind of a proof that we just did right here, if this is true, then that means that the tangent of that angle A would be equal to the tangent of angle D. Now why is that important? Because what this means is for every angle that has a measure of x degrees, we will have the same tangent ratio. Every angle has a measure of x, and x could be 10, x could be 20, x could be 30, x could be any measure. But any angle that has a measure of x degrees will have the same tangent ratio. So for example, up here in this diagram, both angle A and angle D have a measure of 35 degrees. Now if you grab your scientific calculator, there should be a key on your scientific calculator that looks like this. It'll say tangent as a key. If I type in tangent of 35 on my scientific calculator it will tell me that every angle that's 35 degrees will have a tangent ratio equal to about 0.7002. Every 35-degree angle has the same tangent ratio. That's kind of what we proved up here. And that those 35-degree angles all have a tangent ratio of about 0.7002. And that'll be the tangent ratio for both A and D. So, if we know an angle's measure, that means we can use our calculator to determine its tangent ratio. If I know that an angle has a 50-degree measure, I can hit tangent 50 on my calculator, and the tangent of a 50-degree angle is about equal to 1.1918. So that would be the tangent ratio for a 50-degree angle. If I had a different measure that in my picture, I could type tangent whatever, and my calculator will tell me what that tangent ratio is. Does that mean that in this diagram up here, we can figure out the length of AC or BC? Now let's think about that. We know that the tangent of angle A would be equal to BC over AC. We also know that the tangent of angle A is equal to about 0.7002. So if I just take the second two things that are equal right here, and I set them equal, if I say BC over AC equals 0.7002, is that enough information to find out what these numbers would actually be? Or what about DF and EF? Because I know that the tangent of angle D would be EF over DF, and it's also going to be 0.7002. So in other words, EF over DF needs to equal 0.7002. Can I find what one of these is equal to? But if you think about it, the answer is going to have to be no, right? Because in this equation, or in this equation over here, there are two things that I don't know. I don't know BC, and I don't know AC. Or over here, I don't know EF, and I don't know DF. And if there are two unknowns in a single equation, I am not going to be able to find one specific value for each one of those unknowns. There are a lot of different values that would work for this. There are an infinite number of lengths that I could put in for BC and AC, or if I divided those two, I would get 0.7002. There are an infinite number of lengths I could put in for EF and DF, or if I divided those, I would get 0.7002. So the answer here is no. And just to kind of clarify, there are an infinite number of combinations of lengths that would work. And hopefully that makes some sense there. There are an infinite number of combinations of lengths that would work in these two equations. However, what if we knew that AC was 10? So what if we came back to this equation right here? And what if we said that BC over AC, but instead of saying AC, we know that it's 10. We said BC over 10 equals 0.7002. Would this allow us to find the length of BC? And of course the answer is, in this case, yes, because there's only one thing that I don't know. If I know that BC divided by 10 is equal to 0.7002, then that would indicate that if I multiply both sides by 10, if I multiply that by 10 and this by 10, these 10s will cancel out, and it would be BC would be equal to 0.7002 times 10, which is going to be about 7.002, which we'll say about 7.0. If AC was 10, then BC would be about 7. So in that case, we were able to use the information about the tangent ratio and a side length to find another side. So let's look at a couple more examples where we're going to do something like that. We have to find the value of each variable in the equations below. So you can see in A we have a right triangle, or triangle XYZ, and we know one angle measure right here is 40 degrees. We know that this side is 26, and this is the x that we're trying to find. Now, of course, Pythagorean theorem wouldn't work here because I would have another unknown side right here. So I would have two sides that I don't know, so I can't use a squared plus b squared equals c squared. It's not one of the special right triangles that we've learned about. It's not a 45-45-90 or a 30-60-90. But we can use this information about this side, or I'm sorry, this angle measure, and we can set up something like what we did up here to find x. Because if we say that the tangent of x would be equal to segment YZ's length over XZ's length, that's opposite, tangent of x is equal to opposite, which is YZ, over adjacent, which is XZ. We can fill in, there's like three things right here that might be able to be filled in with values, right? The measure of x, the length of YZ, and the length of XZ. We can fill in two of those three with values that we know from the picture. We can say tangent of 40 is equal to YZ, which is going to be an x, over XZ, which is going to be a 26. Now, we know that if I put this over a 1, then I should be able to cross multiply these. X times 1 is equal to 26 times tangent of 40. And again, if I put in my calculator, if I type in tangent of 40 in my calculator, it's going to tell me that the tangent of 40 is about 0.8391. So this is 26 times 0.8391. So x is equal to 26 times 0.8391, and that gives me about 21.8. So x has a value of about 21.8, and I did that just setting up this tangent ratio. In part B, I want to find the f right here. I know that this angle is 70 degrees. I know this side over here. So I can set up tangent of angle G would equal HF over HG. And I can, again, there's three places here where I might be able to put a value, and I know two of them. I can say that the tangent of angle G, which is 70, would equal HF, which is 15, over HG, which is F. If I put this over 1 and cross multiply, I would have 15 times 1 equals F times the tangent of 70. Tangent of 70, and my calculator will tell me what that is. It's about 2.7475. So I have 15 equals F times 2.7475. So if I wanted to find the value of f, I could take both sides and divide by 2.7475. And now f is going to be about 15 divided by 2.7475. Grab my calculator real quick. Tells me that f is going to be about 5.5. So that's one way that we can use this idea of a tangent ratio in a picture, and we can find some missing side lengths using what we know about tangent ratios and how the tangent of a 40-degree angle has a specific value and the tangent of a 70-degree angle has a specific value. We can use that to find angle measures. But there's one more interesting use of tangent ratios. We've determined that since all angles with the same measure have the same tangent ratio, we can use our calculators to determine the tangent ratio of a given angle if we know its measure. Logically, this also means that if we know the tangent ratio for an angle, so in other words, if we know that the tangent of some angle x is equal to, let's say, 0.55555. So we know this is what I get when I do the tangent of angle x. It's 0.5555. We should be able to use our calculators to actually find the measure of that angle. Now what we're going to be doing for this is we're going to be using something called the tangent inverse. And it looks a little bit like this. If the tangent of angle x equals some value a, then if we take what's called the tangent inverse, and it looks like it's usually written as this, tangent with a -1 little exponent there. If we take the tangent inverse of a, that will tell us the measure of angle x. So if, for instance, if the tangent of x equals 0.5555, then if we take the tangent inverse of 0.5555, it tells us the measure of angle x. So if I grab my calculator, now what I'm looking for usually on my calculator is the tangent inverse is going to be found by doing the second, or sometimes it's called the shift function, and then the tangent function, because right above the tangent function what you'll usually see is it'll say tangent -1 like that. So I'm going to grab my calculator and I'm going to do second tangent 0.5555. So let me do that. Second tangent 0.55555, and that tells me that the measure of angle x which is equal to, again, the tangent inverse of 0.5555. It gives me about 29.0 degrees. Right? So that's it. I knew that the tangent of x, let's say, just in some random problem, had this measure. I did the tangent inverse of that number there, and it told me that the measure of x was about 29. There we go, 29.0. So how is that going to end up applying in example problems? Well, over here we have to find the measure of both of these acute angles in this right triangle. We have to find the measure of angle T, so let's put a little T there, and we have to find the measure of angle S. Let's put a little S there. Well, let's start with T. What we know about T is that the opposite side, or the opposite leg, has a length of 6, and that the adjacent leg has a length of 8. So this is my opposite leg, and this is my adjacent leg to angle T. So that means that I actually know that the tangent of angle T is 6/8, which is, you guys might be able to recognize that fraction. It reduces down to 3/4, so it's 0.75, right? So the tangent of angle T is 0.75. Now applying what we just talked about over here, we know that if we do the tangent inverse of 0.75, it should tell us the measure of angle T. So I grab my calculator, and I do tangent inverse of 0.75, and it tells me that measure of angle T is about 36.9, or 36.9 degrees. Now I could do, and for this problem I'm going to do the same thing but with S, right? So now, I'll switch colors real quick. Now for S, the 8 isn't the adjacent anymore. Now it's the opposite, and the 6 is no longer the opposite, it's the adjacent. So the tangent of angle S would be equal to the opposite, which is 8, over the adjacent, which is 6. So 8 divided by 6 doesn't come out quite as nice and neat as 0.75. It comes out as about 1.333, or 1.3 repeating, which I'm going to write down as 1.3333. So if I do the tangent inverse of 1.3333, that should give me the measure of angle S. So tangent inverse of that 1.3333 should give me about a measure of angle S of about 53.1 degrees. So angle T is 36.9 and angle S is 53.1. Now some of you might have realized there was actually a little bit shorter way I could have found this second answer. And I'll show that to you over here in the example B. So in example B I have to find the measure of angle N, and I have to find the measure of angle P. Let's start with angle P. I know that this side over here is my opposite leg, and that this right here is my adjacent leg. So the tangent of angle P would be equal to opposite divided by adjacent. And now 17 divided by 40 gives me actually exactly 0.425. So the tangent of angle P has a value of 0.425. If I do the tangent inverse of 0.425, that should give me the measure of angle P. So on my calculator I do the tangent inverse of 0.425, and it tells me that the measure of angle P is equal to about 23.0 degrees. Now again, I told you there's an easier way that I can get that second acute angle. I need to remember that in a right triangle, these acute angles will be complementary. They add up to 90. So the measure of angle N would be equal to 90 minus the measure of angle P, which we now know has a value of 23.0. So the measure of angle N is 90 minus 23.0, which is 67.0 degrees. And so you can see this idea of a tangent ratio and the fact that all angles with the same measure have the same tangent ratio can allow us to do some kind of interesting things when we know some side lengths, when we want to know an angle measure, like in example 3, or in the case of example 2 up here, when we know an angle measure and one side, we can use tangent ratios to find that other missing side. So hopefully this stuff makes sense to you. If not, you can always go back and rewind the parts that are still a little bit confusing, and we will see you next time.